Alright, so we're going to go over test 7 from this year for number sense. We're just going to go down the line. We might not do all 80 today, but for sure we're going to do the first page. Okay, so for number 1, we're just going to add one digit at a time. So 6, 6, 6, and 6. Okay, number 2, you want to be careful here when subtracting. So I have a 1 minus a 3. So I got to carry 1 from 2. This turns to an 11. So 11 minus 3 is 8. And I have 1 minus 2, but I can't do that. So I got to carry an extra 10 from the 7. So I have 11 minus 2, that's 9. 6 minus 4 is 2. Or what you could see is I can do 21 minus 23, and that's going to be negative 2. So that's like 2 under 100, right? So it'd be like 98. And then I have the 7 minus the 4. But I also subtract an additional 1 because I went under 100 for that last step. So I also still end up with 298. All right, so number 3, you want to turn this into a an improper fraction here. So I'm dividing by 7 over 2. So we're just going to do keep change flip. So 15 times 2 over 7, it's the same thing as 30 over 7. And 7 goes to 34 times with a remainder of 2. So as a mixed number, this is 4 and 2 over 7. Okay, number 4, we're just going to do the 75 trick. So we're going to take 28 and multiply by 3/4, and then multiply by 100. So I'll divide by 4 first. I get 7 times 3, which is 21, times 100 is 2100. So 3/4, 28 is 21, times 100, so I just add 2 zeros at the end. Okay, for number 5, you want to have your squares up to 30 memorized. The squares up to 30. But if you don't have your squares memorized, you could always do FOIL. And so what FOIL is a strategy to multiply any 2-digit number. So let me just make up an example here. Say I want to multiply 36 times 53. FOIL works by taking these first, like 1 units digits. So I'll multiply those. So 6 times the 3, that is 18. But I only write down the 8. I'm going to carry the 1. And then I get the product of the inner and outer terms. So that would be 30 and 9. I add those together. I get 39 plus the 1 that I carried. It's going to be 40. So I'll write down 0 and carry 4. Now I do my last step, which is to do these last digits here, these tens digits, get their product, which is going to be 15. And then I carry on that 1 from earlier. That 4 from earlier, my bad. So I add on to the 15 and get 19. And so that's going to be my answer. And so you're going to do the same trick with 23 in your head. 23 times 23. I multiply the units digits, I get 9. I don't have anything to carry, so I just move on to the next step. Note that when I have a number that I'm squaring, I'm going to have these same two digits, like the product of the inner and outer is going to be the same. 3 times 2 is 6, and 2 times 3 is 6. So you could just do 2 times the tens digit times the units digit. And that's going to be the sum of the inner and outer terms. And so that's going to be 12. So I write down the 2, and I carry the 1. Lastly, I multiply the tens digits. I get 2 times 2 plus the 1 I carried. It's 5. So my answer is 529. Number 6. So here it's asking about powers of 10. I'm just subtracting these. So I have 1,000 here. 10 to the 0. Anything to the 0th power is 1. And 10 squared is 100. So this is going to be like the same thing as 900 minus 1. So it's going to be 899. Number 7. So both the 17 and the 22 are being multiplied by a factor of 13. And so we can factor that factor 13 out from both expressions. I can get that this expression is equivalent to 13 times 17 minus 22. Right? Because if I distributed this, I would get 13 times 17 minus 13 times 22, which is this expression here in the problem. But this is easier to calculate because I know what 17 minus 22 is. That's just negative 5. And so I'll just simply multiply these and I get negative 65. Question 8. 3 3/4%. We want to convert this to a fraction. So whenever you want to convert a mixed number percent into a fraction, you need to turn this mixed number into an improper fraction and then divide by 100. So let me show what I mean with an example. Say I had 4 1/4%, and I wanted this as a fraction. So I convert the 4 1/4 into an improper fraction. The way I do that is I take my denominator and multiply it by this number. And then I add that product to the numerator. Okay, so 4 times 4 plus 1, that's 17 over 4. And now I divide by 100, which is the same as adding 2 zeros on the bottom. That's my answer. But you need to be careful in case something simplifies. And so if I had 4 1/6%, this would turn into 25 over 600. But this fraction will simplify. So before you write down anything on your test, think about what it's going to look like before you simplify. So you do the trick in your head, you get 25 over 600, and think about how that reduces. And you'll get that that's equivalent to 1 over 24. So let's do it with this problem. 3 1/4, or 3 3/4%. So I do my trick, I multiply and add. I get 15 on the top and 400 on the bottom. But this will simplify. Both the numerator and denominator are divisible by 5. So this fraction is the same as 3 over 80. And it doesn't simplify any further, so that's our answer. For number 9, we just want to evaluate it. So 36 over 9, 4. 36 times 2 is 72. I subtract, I get negative 68. Okay, for number 10, whenever you have a question, a little asterisk or star next to it, this is an estimation question, meaning you have to be within 5% of the actual answer. So if I had an answer of 1,000, then anything in the range from 950 to 1,050 would be acceptable as the correct answer. And so you can get away with rounding on these. So I would probably round this number to 300, and I would keep this number about the same by saying it's 790. So I rounded up here, and I rounded down a bit here. So this is the same as doing 3 times 79 times 1,000, or just adding 3 zeros. So 3 times 79 going to be 237, and then I add my 3 zeros back. I get 237,000, which is in the middle of that range. Okay, so for number 11, you could just do long division, and you'll get 48. Or you could see that, if there's nothing here that specifies it's a mixed number or an improper, you know that the result has to end in an 8. And this number in front can't be a 5, because if I did the 11's trick, I would get a number that's greater than 500. It would have like a 6 in front. It'd be like 638. So this digit has to be a 4. So that when I do the 11's trick, this hundredths digit comes out to a 5. For number 12, I want to find the greatest common denominator of these 3 numbers. And so I start thinking about what factors these guys have. So I see there's a common factor of 3 in all of these. I see that, okay, they have a common factor of 9 as well. That's greater. So I forget the 3. And there's nothing else that they have in common. Because when I take away 9 from these, I'm left with 3, 5, and 7. So they share no other factors in common. So I get 9. 13 is a dimensional analysis question. So there is 12 inches in 1 foot. So when I square these units to get inches squared, I find that there is 144 square inches in 1 square foot. And this makes sense because if I had, say, a 3 by 3 square like this, so say this was 3 feet and 3 feet, then here I'd have 12 inches, 12 inches, 12 inches. And so I'd have 36 times 36 representing the area in square inches. Whereas in feet, it would just be 3 times 3. And so this extra scale factor between inches and feet of 12 is multiplied twice. So in this example where I'm scaling a 1D thing, like length, my scale factor is just S. But when I have a 2D entity, like area, my scale factor is S squared. So here I have 3 square feet, and I know that the scale factor from feet to inches is 12. And because I want square feet and square inches, that tells me I gotta multiply by the scale factor squared. So I'd have 3 times 144, which is 432. For 14, this is the 15s trick. The 15s trick works by taking this number, which is not 15, halving it, so I'd get 16, adding it with the original number, so 32, I'd get 48, and multiplying by 10, or just adding a 0. And so let's do that same trick with 88. I have 15 times 88. I'll add 88 with half of itself, so 44, and I get 132. And now I multiply by 10, which is the same thing as adding a 0 at the end. Number 15. So for 15, we want to do a trick that uses modular arithmetic. And that just means we look at the remainders. So let me write the expression here. So instead of adding these numbers and then dividing by 4, what I could do is I can see what the remainder of each of these numbers are individually, and then add those remainders. And that would be the same answer as if I added these numbers first and then got the remainder. So what's the remainder of 31 being divided by 4? It's going to have a remainder of 3. But you could think of a remainder of 3 as being equal to a remainder of -1, because it's 1 away, or 1 less than another multiple of 4. So I'm going to treat this like it has a remainder of -1. And so I'm just going to assign this value of -1. In more fancy terms, we'd call this, we'd say 51 is equal to -1 mod 4. Mod being modulus, which is the same as a remainder. So a remainder of -1 when divided by 4. So this is -1, and do the same thing for 123. And that's also going to have a remainder of -1. And now I'll just add these two. Now get -2. So this whole expression here has a remainder of -2, but I can't put that as my answer choice. Instead, I just put 2. Because a remainder of -2, so -2 mod 4, is equal to 2 mod 4. Number 16. So this is a proportion question. So I can set up this proportion. So if 8 abs cost $1.20, then 12 abs costs how much? So I could see I'm scaling by a factor of 1.5. I can scale up here too. So I'll just multiply 1.2 times 1.5, and I get $1.80. For 17, the trick when adding consecutive odd numbers is to take your last number. So let me do an example. Let's say I'm summing the odd numbers from 1 to 13. To get the sum, I take the last number, add 1, divide by 2, and square. So I add 1, I get 14. Divide by 2, that's 7. I square 7, I get 49. It may look like a lot of steps, but there are a lot of quick steps. Let's try and do this question as fast as we can. Ready? So 35 plus 1 is 36, divided by 2 is 18, squared is 324. Again, it helps to have your squares memorized, 1 to 30. If you didn't have it memorized, you would have to do FOIL. 18. Whenever you see two square numbers being subtracted, you want to immediately think about the difference of squares. So you might have learned in Algebra 1 if you've taken it, that the difference of two squares is equal to the sum of the two numbers times the difference of the two numbers. So I can break up a complicated looking question, such as this, into something easier, because this expression should be equivalent to their sum, just 340, times their difference of 2. Let's try it with this question. So this expression here should be equal to the sum, which is 120, times their difference, which is 8. And the question tells me that this is equal to 12 times some number. I'll just put a question mark here. To solve for that question mark, I'll just divide by 12 on both sides. This goes away. I could take out a factor of 12. Here, I'll be left with 10 times 8. I get 80 as my answer. Just doing some algebra. Pause. Hey Mom, I'm busy. I'm recording a video. Oops. Sorry. 9. Okay, come back now. Question 19. So this is another proportion question. So if 1 inch is equal to 2.54 centimeters, and 508 centimeters is equal to how many inches? So hopefully you can see that I'm scaling here by a factor of 200. And so I'm just going to scale here by that same factor. So I get 200 inches. Number 20, it's another estimation. So I have 16 times 18. And so this product I can estimate is about 17 squared. Which is 289. And that is about 290. So I'm going to take 290 and square that. And that's the same as doing 29 squared times 10 squared. Or just doing 29 squared and adding 2 zeros at the end. 29 squared is 841. And then now add 2 zeros. And that's in the range. So here I have 1/9 and 1/27. So to add these, I want to make the 1/9 have the same denominator as the 1/27. So 1/9 is the same as 3/27. I'll add that with the 1 over 27, and I'll be left with 4 over 27. That's the first column. Okay, 22. The mean of 33, 25, 39, and 31 is. So we'll just add all these numbers and divide by 4. We just sum these elements and divide by how many elements there are. And so when adding these, you want to add smart. So I see that this 39 plus this 31 is going to come out to a nice clean 70. So I'll add those first. Then I'll add 25. That'd be 95. Then I add the 133. And that's going to be 128 divided by 4 is just 32. 23. 24 less 25% of 44. Less means the same thing as minus. So 24 minus a quarter of 44, which is just 11. That's just 13. $24. So 24 is 2 tricks combined in one. The first trick is difference of squares. And the way that works is because 55 squared minus 2 squared is the same as this expression. Because if you remember from earlier, it should be equal to the sum of the two numbers. So 57 times their difference, 53. And the way to quickly spot what those two square numbers I'm subtracting are is what number is in the middle of these two numbers, so 55, and how far apart are they from each of these numbers. So it's a distance of 2 away. In this case, doing 55 squared minus 2 squared is actually easier than doing 53 times 57. But how do I do 55 squared quickly? And that brings us to the second trick to know, which is how to square numbers that end in 5. I'll use 25 as an example. So whenever you're squaring a number that ends in 5, you want to write down 25 at the end. Now the number in front is going to be this number in front of 5, so 2, times 1 more than itself. So 2 times 3, that's 6. Let's try another example. Say I had 45. So I'd write down 25 at the end, and I'd do 4 times 1 more than itself, so 4 times 5, and that's 20. And that's the answer. So now, let's combine both these tricks we just learned into one quickly. So this expression is the same as 55 squared minus 2 squared because the number in the middle of these two numbers is 55, and 55 is 2 away from each of the numbers. I need to do 55 squared minus 2 squared. And 55 squared is going to be 3025, because it ends in 25, and the front is 5 times 6, so 30. So 3025 is 55 squared, minus 2 squared is 4, leaving me with 3021. Number 25. So this little 8 means base 8. So the number system that we use has certain place values. It has the ones place, which is 10 to the 0, the tens place, which is 10 to the first, the hundreds place, which is 10 squared, and the thousands place, which is 10 cubed, and so on. So the number system that we use is base 10. And so every number that we can write, such as 512, can be written in the form 5 times 10 squared plus 1 times 10 to the first plus 2 times 10 to the 0. And so what a different base system like base 8 does, instead of having a tens place and a hundreds place, well, they still have a ones place. 8 to the 0 is 1. Then they have an 8's place, and a 64's place, and a 512's place, and so on. And that's how they express numbers in that system. And so the trick for quickly converting from one base back to base 10 is to multiply. Like you take this first number here, you multiply by 8, then you add that product to this next number. You take that sum, then you multiply that by 8, and then you add that product to the next number, and you keep repeating until you're done. Let's do this in action. So 2 times the 8 is 16, plus the 5 is 21, times the 8 is 168, plus the 2 is 170. Number 26. The larger root of x squared minus 2x minus 24 is equal to 0 is, so you want to factor this expression. So you want to think, what two numbers multiply to negative 24 and add to negative 2? And so those two numbers are negative 6 and positive 4. That means my factors are going to be x minus 6 and x plus 4. That will be equal to this expression. And so now I can solve for my roots by setting each of these factors equal to 0. So x minus 6 equals 0, x plus 4 equals 0. Now I solve for x, and I get that x is equal to negative 4 and 6. and the larger one is 6. So 6 is my answer. If you wanted the smaller root, -4 would be the answer. -27. So a good trick to have in mind is for squares close to 50. So let's take 57 as an example. The trick works by, first I square the units digit, so I square 7, and I get 49. And to get the remaining part, I take 25 and I add on this digit. So I add 7. And I get 32. Now what if I had a number that was less than 30? So let's try with 47 squared. So I'd start off by doing 7 squared. Wait, no, my bad. I see what the difference between 50 and this number is. That's 3. And so I'm going to square that. So I get 09 here. Right, the 0 and 9, 2 digits. And we're going to take this difference of 3 and subtract it from 25. And get 22. And that's my answer. So this trick only works for numbers from about 40 to 60. So there's no need to memorize those squares, just this trick. So let's do the trick for 54. So it's going to end in 4 squared, 16. And the front part is going to be 15 plus this 4. So 29. So 25 plus the 4. 29. 28. So the thing to know about these type of questions, because they appear on almost every test, is you want to see what factor you have here. So in this case, it's 6. It's being multiplied to this awkward number here. And you want to factor out a 6 from here. And get that this is the same as 5 times 6. And so really, this expression is the same as 1195 times 6 plus 5 times 6. And that's really the same as 6 times 1200. And that's just 7200. Now, one quick way to solve all these questions is to just round up to 1200 and then multiply by 6. So that's just a quick way of doing it. 29. So how many prime numbers divide 72? Let's break up 72. Let's do the prime factorization. And the way we do the prime factorization is we make a factor tree. So 72 breaks up into 8 and 9. 8 breaks up into 4 and 2. 4 breaks up into 2 and 2. I stop once I reach a prime number, so I can't separate it any further. So on this side, I have 3 and 3. Those are both prime numbers. And now I'm done. So I count up the primes that I do have. I have 3 2s and 2 3s. So I would say that 72 is equal to 2 times 2 times 2 times 3 times 3. Or 72 is equal to 2 cubed times 3 squared. Of course, you would do this on your head though. So how many prime numbers divide 72? Well, from our factor tree, the only prime numbers we had were 2 and 3. So the answer is just 2. Third, so we're estimating this square root. And so the trick for estimating square roots now, make an example here. Let's say I wanted to estimate 5698. So this is tough to think about. So instead, what I can do, I can eliminate 2 digits and think about what the square root of 56 is in between. And I know that has to be between 7 and 8 because 56 is between 7 squared, which is 49, and 8 squared, which is 64. And now I want to think, which number is that closer to? In this case, it's about in the middle. So I would estimate that this is about 7.5. Like that would be about what the square root of 56 is. But because I eliminated these 2 digits, that's the same thing as eliminating a factor of 10. So this would be about 75. Which is pretty close because the actual square root is about 75.485. Let's do one more example. Let's say I had the square root of 22,559,999. So I can eliminate 2 digits, but thinking about what this square is between is tough. So I can eliminate another 2 digits, and then another 2, and now I'm just estimating the square root of 22. And I know it has to be between 4 and 5 because 22 is greater than 4 squared, which is 16, and less than 5 squared, which is 25. Now I think about which number it's closer to. It's closer to 5 squared. So it's probably a bit more than 4.5. I would say it's about 4.7. But I eliminated 3 factors of 10. I got to move the decimal to the right 1, 2, 3 times. And so I get that this square root here is about 4,700, which is close because the actual answer is about 4,750. So it's within 5% of the actual answer. So now let's evaluate this question. So I'll eliminate 2 factors of 2, and then again, and now I have 119. And I know this square is between 10 and 11 because it's 119 is between the squares of those two numbers. It should be just 100 and 121. And it's definitely closer to 11 squared. So the square root's probably about 10.9. But I need to shift the decimal spot twice to the right because I eliminated 2 factors of 10. And so I get that the square root is about 1090. So I have 2.022 repeating. And I want this expressed as a mixed number. So I can start off by putting a 2 on the side. Now I need to know how I can represent this 0.022222 as a fraction. So the 2 common fractions you want to have memorized are or tricks I would have memorized. Oops. It's the x over 99 trick and the x over 90 trick. So if you see a number that has 2 repeating digits, like 15, 15, 15, so 0.15 repeating, this low line means that the number repeats. Then you're going to do the x over 99 trick. So this decimal here is equal to 15 over 99, which would just simplify to 5 over 33. But what if only one digit was repeating? What if I had 0.15555, or just 0.15 repeating? In this case, I would do the 1 over the x over 90 trick. And so the number that's on top would be this part right here before it repeats, so the 15 minus the non-repeating digit, which is 1, all over 90. So that would be 14 over 90, which is 7 over 45. So let's think about what case this is. We have 0.022222. And so we'd use the x over 90 trick. So we do these two digits, so just 02, minus the non-repeating, which is just 0, all over 90. That's 2 over 90, which simplifies to 1 over 45. And so that's the fraction part of our answer. Number 32. So here we have a system of equations, and I want to solve for x squared. So when solving systems of equations for number sense, you always want to use elimination. I might have spelled that wrong. I'm not sure. And so I want to cancel out the y's. So I'm just left with my value of x. So let me write these two equations on top of each other. So one way I could cancel is I could multiply this top equation by -2, giving me -4x minus 2y equals -20. And now add this whole equation with the second equation. This way, these y's cancel out. The bottom here, I would get -3x plus 0 equals -9. And so x is equal to 3. So x squared is equal to 9. That would be my answer. Number 33. So here, we just want to do FOIL. But instead of having a units digit and a tens digit, like in this example, I have a fraction part and a whole number part. And the trick works the exact same way. So I do the 1/4 times the 1/4, and I get 1 over 16. I'm going to add the sum of the inner and outer products. So that would be 2 and 1. But I'm going to add that as well to the products. So I don't write the sum yet. So whenever I'm doing this with fractions, you got to add the sum of the inner, outer, and the integer products. So 32 plus 2 plus 1 is 35. That's my answer. Number 34. So I have a sequence, and I don't know what the values of a and b are. And I want to get the sum. So I got to find what the sequence is. I could see that this is an increase of 2. This is an increase of 3. This is an increase of 4, 5. And so I see a pattern here. So this is probably going to be an increase of 6. So this number should be 21. This is an increase of 7. So this should be an increase of 8. So this should be 36. So I'll add those two numbers and I get 57 as my answer. So you want to be able to spot patterns. Another thing you could have realized is that these are just the triangular numbers. And the triangular numbers follow the formula n times n plus 1 over 2. And so here I have the 6th and 8th triangular number. So I'd plug in 6 here. I'd get 6 times 7 over 2, which is 21. And the 8th triangular number, which is 8 times 9 over 2, which is 36. I get the same numbers for A and B as before. Number 35. So the thing to know here is that this whole sequence is the same as if I did all those operations and then squared at the end. So this would just be 3 squared, which is 9. So I don't have to do 144 divided by 36 times 2.25. So that makes it a bit easier. $36. So here, I'm going to do FOIL again, just like the last one. So if you want, you could pause the video and try this on your own. If not, I'll just solve it right now. We multiply the fractions. We get 3/5. And now we sum the inner, outer, and integer parts. So I get 8, 6, and 80, which sums to 94. So my answer is 94 and 3/5. Number 37. So I have this quadratic expression, and I'm told that the sum of the roots is -5. So the thing to know is that the sum of the roots is equal to -b over a. When your quadratic is in the form ax squared plus bx plus c equals 0. And a and b and c are your coefficients. Your product, this is useful to know in case it asks. Your product is c over a. And so The sum of the roots is negative b over a. So that's negative k over 1 is equal to negative 5. So k is just 5. Again, should know that from Algebra 1. Number 38. So, unlike this last question, in 25, we're converting from base 8 to base 10. In 38, we're converting from base 10 to base 8. And so the way we do that is we're going to do long division. So you'll divide. So this goes in 4 times. And 1 time with a remainder of 5. So after we divide by 8, which is our base, we get 41 with a remainder of 5. And so we're going to write down what our remainder was. So the 5. We're going to take this 41 and we're going to do long division with that quotient now. So the 41 is going to be divided by 8. It's going to go in 5 times with a remainder of 1. So I write down the remainder and I keep repeating this process. So now 8 does not go into 5. So I'm done. So I just write 5. So 515 is my answer. And let's try a similar question. Let's say I'm converting 278 base 10 into base 6. So I'll do long division. Of course, this is all in your head. I get 46 with a remainder of 2. So I write the 2, and now I'm dividing the 46. So that's 7 with a remainder of 4. So I write the 4. Now I do the 7. It goes in 1 time with a remainder of 1. I write 1. Then 6 does not go into 1. So I write 1. So this right here is the over and under 100s trick. So I have one number which is under 100 and one number which is over 100. So I want to see how far away these numbers are from 100. This one is 5 less, and this one is 2 times greater. And so I'm going to take the product of negative 5 and positive 2, which is negative 10, and I subtract that from 100, which gives me 90. And this is what the end part of my answer is going to be. To get the front part, I take these same 2 numbers, and now I add them, and I get negative 3. And I subtract, I add that negative 3 to 99. and I get 96. So that's my answer. Let's try that with another example. Let's say I add 94 times 104. So this is 6 less and 4 greater than 100. So their product would be negative 24. And I add that to 100. So I add this negative 24 to 100, and I get 76. So that's the end part of my answer. Now I add 6 and the negative 4, I get negative 2. And I add that negative 2 to 99. And I get 97 as my front part of my answer. Number 40. So I'm dividing here. I wouldn't really estimate. Like I wouldn't round, I mean. I just do like long division twice and then write zeros at the end from there. I wouldn't do like a full long division. So for sure, this goes in once. And then it would go in an eighth time. And now I just write a 0. And the reason I'm saying that is because as I do long division, it goes in once, drop down to 1, and it goes in 8 times. But instead of continuing the long division, I'll just put a 0. And I'll be done. Well, my bad. 2 zeros. Make sure you put the right amount of zeros. So 1800 is my estimate, which is my answer. It's in the range. So it works. Okay, 41. 32 has how many positive integral divisors? So the trick to tell how many positive integral divisors a number has, yeah, I'll show an example with 36. So after you do the prime factorization, you should get 2 squared times 3 squared. And what we're going to do is we're going to look at these exponents. We're going to add 1 to both of these. And I get 3 and 3. And I multiply, and my product is the amount of integral divisors of 36 I have. Those being 1, 2, 3, 4, 6, 9, 12, 18, and 36. And so I'll do the same thing with 32. 32 is unique because it's a power of 2. It's actually 2 to the 5th. So all I have to do is just add 1. I get 6. So there are 6 positive integral divisors. Those being 1, 2, 4, 8, 16, and 32. Number 42, add 7 cubed minus 2, and I want this represented in base 7. So remember that in base 7, the place values are the 7 to the 0, 7 to the first, 7 squared, and 7 cubed. So this number right here is actually 1000 base 7. And I'm subtracting 2 base 7. Because 2 base 10 is the same as 2 base 7. And so I'll just subtract these numbers in base 7. But keep in mind that subtraction works a bit differently. So in the regular base system, in base 10, if I were to subtract 21 and 3, I'd have to borrow 10 from this place value here. So I can do 11 minus 3. I get 8, and then the 1, right? And you'll do the same thing in base 7. Like, let me do an example. 71, 101 minus 3, base 7. So I can't do 1 minus 3. So what I'll do is I'll borrow from here and turn this into a 7. And then I'll borrow from there and turn this into an 8. See what I did there? I'm adding 7. So instead of adding 10, instead of turning this 1 to an 11, it turns the 1 to an 8. So now I can subtract. I'd be left with 65. Now let's do this with these two numbers. If I borrow from here, it would go to 0. This would go to 7. I'd borrow from there, this would go to 7. I'd borrow from there, and this would go to 6, and this would go to 7. And so I'd be left with 665. That's my answer. Or, I guess it's also just easier to know that 1 less than this number would be 666, and then 665, 664, yada yada. So that's page 1 of this number sense test solved. Maybe we'll do page 2 another day, but hopefully you learned some new tricks. And so I'll see you guys later.